So this is taking a look at when the area is from a known cross-section. So far our technique has been, when we revolve it, it's a disc or a shell, and really that's a known cross-section. We just happen to know that it's a disc or a shell. So today we're going to look at what happens if you have a figure, and if you sliced it one way, you'd always get the same type of shape. So here's what I mean is, this first one, you can see the shaded area here. This is the graphs that we'd be looking at, and you're going to see this when we look at the questions. Here's the x-axis. This means the cross-section is perpendicular to the axes, the x-axis, and it's a square. So no matter where I move it, it changes size because it's using the parabola and this line up here as the bounds. But that's what determines how big that square gets or how small it is. Now, this one's trickier to visualize, but if you want to think about what it looks like, this is what you'd see from that figure. So let me just, I guess I can't really hide that one, but maybe I'll move it all the way on this side. So today we're going to look at, well, that's not bad there. So today we're going to look at these different figures. Like, the shape is very intimidating, but for us, it's a square at each case. So it's not so bad to find the area of a square. And we could do other things like, we could do, why don't we do equilateral triangle? And that changes the shape slightly. So that means all the three lengths are the same size, and I move it along. Just an equilateral triangle everywhere, and it would make this kind of a figure that I'd be trying to find the volume for. So we're adding all the slices of those triangles, or those squares, all these known shapes. So another common one, just to help you visualize it, isosceles right triangle, and it usually uses one like this, where the legs are on the bottom, and you know, when you generate that, you get kind of a nice shape out of it too. Or what's this one? Turned the other way. Yeah, with the bottom facing that way. And it could be that the hypotenuse is on the bottom, just changes the shape slightly. What else we got here? Oh, semicircles are pretty common. We'll try that as our last one, but a semicircle meaning that the shape that goes between them, just a half a circle. So if we want to generate the solid, get this kind of a shape out of it. So we're going to take a look now at the calculus that helps us generate these volumes. But again, it's very helpful to picture what you're doing, and we will have lots of pictures in this to get us through it. So this is the basic, and this is what you've already been doing. It's just now we're talking about it generically. The area we're integrating. If we integrate each slice of area, then we end up with the volume, right? It's kind of like if I had a stack of papers. Each paper, I mean, it does have some volume in the paper, right? We won't argue about the theory there. But you could picture each page is like a sliver, like a square, like the area. If you added up all of the squares in that bundle of paper, you'd get the volume of the whole thing. So that's what we're really doing here. Now, we're going to take a look at, I'll bring up my graphing calculator so you can see it. So 4 minus x squared. And I'll zoom in a little bit so you can see it better. Okay, so it is actually a circle. My screen isn't quite square. That's why it's a little distorted. But it says here we're going to take this, and every cross section is also quadrant 1. So we're only looking at the area in here. And it says every cross section perpendicular to the x-axis is a square. So I will let me try and make a better circle out of this. Anyway, I will try and get a picture that we can work on. So this is what my figure, this is what I'm looking for. And I'm taking it perpendicular to the x-axis. So if you draw one of the representative squares, it would look like this. perpendicular to the x-axis. And you have to do your best to imagine my terrible three-dimensional drawing skills, but it's basically coming out like that. It's like you got 3D glasses on, right? No. Okay. So this would be coming up out of your page, this square. And if we want to know what's the volume, we have to come up with an area function. So the volume is going to be the integral. We're going from 0 all the way to 2. And I'm going to say it for you as well, just so that you keep thinking about it. This equation is with respect to x, and these bars here would be also with respect to x. This is a dx problem. So everything's set up that way. I'll need my area in terms of x. Okay, we could turn this thing around and look for the area with respect to y. But in this case, the way it's set up, it makes sense to use dx. So can somebody give me an idea here? I'll take the easy one. You guys can figure out the other piece. It's not too bad for this first one. So the area is just going to be, it's a square. You take the side length and you square it. So can anybody come up with that function then for the area of a square? Or these particular squares? Yeah, so you've actually got the whole answer there. It'll be 4 minus x squared, whole thing squared. So we just have 4 minus x squared. This height here, one of the sides of my square is root 4 minus x squared. So because one of them is that, I just multiply the two together. Just a second there, Leo. This side of the square that's coming out of the page, it would also be 4 minus x squared because we know it's a square. They have the same length all around. So multiply them together, I get the area function. This is what I'd be using to find my volume. It's the integral from 0 to 2 of 4 minus x squared dx. So that'll be 4x minus x cubed over 3 from 0 to 2. Okay, so this time we've got a solid with a base bounded by that line. Well, there's 3 lines there. So I'll get you a picture here to work with. X plus 2y equals 6. X equals 0 and y equals 0. Okay.
Just to be clear, we cannot put y in the TI-83.
No, your TI-83 can't do that magic, so unfortunately you're going to have to sweat it out and rearrange it. But if you have your TI-83, it's not the end of the world. It just means you'd go x plus 2y is a 6. 2y is negative x plus 6, so y will be negative 1/2 x plus 3. So you'd have to just do that little bit extra to get it in your calculator. But let's be honest, if this were in your AP exam, you're probably going to have to do this one by hand. It's just a line. You'd be expected to know how to draw that line, so they wouldn't expect you to rely on a graphing calculator for that. And if that's not true, go find your Math 10 teacher and wag your finger at how you've forgotten how to do a line. Okay, the picture here, there we go. So I'll copy this and put it into, just to save you the agony of my crooked lines, and let's see where we end up. So that's, so there's my graph. And it says that they're still perpendicular to the x-axis, and I'm actually going to make a slight change to this. I'm going to turn this into semicircles. We could do circles, but let's try a semicircle. So the first, like honestly, I don't know how to do these until I draw a really good picture of what's happening, and then I figure out what my integral is from the picture. So here I'm going to do my best to try and come up with a semicircle. It's perpendicular to the x-axis. So if I drew it here, there's one of my slices. So just for your own benefit, try and visualize what you think this is going to look like three-dimensionally, and then I'll draw for you my really lame attempt at that. So if that's what's perpendicular, it would be coming up out of my page like this. And that would be the jumping out part, the three-dimensional jutting out of your page semicircle. Okay. So if I'm looking for my area function, I'm talking about the area of a semicircle. So what's the area of a semicircle?
Pi r squared divided by 2.
Yeah, so pi r squared divided by 2. So what I need is, how do you get the radius? Here's the radius. Maybe I'll pick a different color. Let's try purple. So if that was my radius, can anybody describe how to find that radius?
Function divided by 2.
Yeah, it's the function's height divided by 2. This would be the entire function, but that would be the diameter of the circle. So I don't want to use the entire thing. I only want to use half to get the radius. So in this case, my area function is going to be, and we've already solved it here, pi negative 1/2 x plus 3 squared over 2. And this radius inside here, I didn't really leave a good room. I'm going to have to, should have left a little bit more room. It's this line divided by 2 to get the radius. As it is, it was a diameter. So I'll just show you what happens here then. I could simplify this a little bit. The squared on the bottom will become a 4. So it would be pi times negative 1/2 x plus 3 squared over 8. I mean, you could keep going with it, but I guess at this point we can probably just, we can start our integral to see what it would look like. This will be the integral. The bounds are this area in here. And we go from 0 to 6. So I'll take my constant out front, which was pi over 8. And I'd have negative 1/2 x plus 3 squared dx. So I'm going to want to expand that to help me work out what it'll be. So it'll be 1/4 x squared. Let's see here. Minus 3 x's plus 9. So I think that's the integral I'm looking for here. So again, at this point in our calculus careers, I'm hoping that I can leave you to do that integral of a power rule backwards, and we can just focus our time on finding these three-dimensional integrals. Any objections to that? Oh, yes?
The question is,
Question,
how
okay.
does this thing look like?
How does it look like?
Yeah, like before the one we did with dish and washer, we know it rotate around something, right? But
Yeah.
how does this thing rotate or expand?
It doesn't rotate. It is a solid. It is a solid that when you... so before, the reason we had to rotate it was that got us from 2 dimensions into 3.
Yeah.
This one is saying, I have a solid, and they're describing what the solid looks like to you. So the solid already exists. It doesn't need to be revolved or rotated. And there's telling you that the bottom of the solid, so picture it sitting on your table. These cross-hatchings is the part touching the bottom of the table, right? The part coming up off the table are the semicircles. So the best that I could describe it to you is, you know the cotton candy things that you hold? The paper cotton candy? Yeah, people know what I'm talking about, those cones? Or like even a cup, like a paper cup. If you were to cut that in half and stick it on the desk, that's kind of like what this would look like. Not exactly because, obviously the cup is a proper triangle. Like it's a little bit different, but if you're trying to visualize it, that's probably the closest thing I could explain to you. It'd be like a paper cup or the cotton candy holders. Okay. Good, though. You should always try to visualize because it will help you answer what the integrals are here. Okay, so I guess we'll do this. You know what? Actually, no. I'm going to do... I would like you to set up your picture for me. I'll help you with the triangle part of this, the equilateral triangles. But try setting up your picture, and then I'll come around and see how you're doing. All right, so I'll show you the picture that we would have had here. X plus y, y equals 4. And just change this a little bit. You don't really need to write these ones down, but I will. So this is my picture to work with. And it says every cross-section perpendicular to the x-axis, they're equilateral triangles. So, you know, again, I'll do my best with it, but if I go perpendicular to the x-axis, that means what I'm going to get is a triangle whose sides are also that same length. So something like this. So it's very similar to the last shape that we worked on, except triangles will make it a sharp edge rather than a nice round smooth edge. So in this case, to figure out what that integral is, our area function is going to be the area of an equilateral triangle. So the area for a triangle is 1/2 the base times the height. And one of those is quite easy. The base, yes, the base is right here. So I know that's going to be 1/2. This is y equals negative x plus 4. So negative x plus 4 will be here times the height. Now the height is a little trickier, but does anybody recognize this? Equilateral triangles, you can kind of use Pythagoras. We've seen this before somewhere, like hint, hint, your math 12 teacher taught you something about this.
Oh, you mean the 45, 45?
Yeah, these are some of the special triangles. This is a 60, 60, 60. So if I wanted to come up with an equilateral triangle, this is 60 degrees in here, right? And we're used to chopping it off like that. So this is the height here. This h, that's the height you're used to finding. Sorry, whoops. That's the height you're used to finding from when we did trig. So 30's up here. And do you remember what these lengths were when we did it? Sure. So in my picture, what you normally would have had here, the one you're used to using, there'd be a 2 here, a 1 here, and a root 3. But that's not the proportions in this picture because that would mean the triangle was the same every time. So if I look at what I've actually got, this is actually half of my base, right? So this here, this root 3, if I wanted to know what is this, I know that's half the base. What's the height then? Well, the tangent of 60 is equal to the height divided by half my base. So now I get half my base, tangent of 60, equals the height. And I can find the tangent of 60 by using the same triangle. Opposite over adjacent, that's going to be root 3. So the height is going to be almost the same thing. It's just I've got this root 3 over 2. So that area function would be root 3 over 4 and negative x plus 4 squared. Well, we did kind of use Pythagoras, right, as part of our special triangles. I'd love to see if you have another technique for doing it. This is just the first one that comes to mind for me. Now, I would say that typically this is the hardest of the cross sections because there's that extra calculation step. Because if I told you it was isosceles, you'd know how tall it was. You've already got one of the lengths there. So anyway, we'll try an isosceles one. You'll see it's a little easier, but as long as that didn't blow your lid, that's the worst it gets as far as an area formula goes. And the trick is to use the triangle you know from trig to get there. So we'll just write up our integral. We won't calculate it, but it's from 0 to 4 of root 3 over 4 negative x plus 4 squared dx. So that would give us my volume here. Okay. So picture, picture, picture. I'd like you to try this one and see if you can conquer it. This time we're going perpendicular to the y-axis. So think about what that means. But it's pretty much identical to the ones we've done, only now I'm trying to see, can you adjust your thinking if you go perpendicular to the y-axis? So I do have a graph for you to take a look at, and I will just use this here for our discussion. So the first thing that I want to do is make my representative region so that I can figure out how I have to approach the problem. When you do disc and washer and shell, it's a rotation. You have the option of thinking about which one is better, the shell or the disc method. There's no rotation here. It is what it is. It is a solid who's perpendicular to the y-axis. So I have to draw it this way. And that would be my slice, my cross section. And this is with respect to y. So because it's vertical like this, it's a dy bar. That sliver is going to go to 0. So that means I need this here to be with respect to y. So y minus 1 is x squared. So x would be plus or minus y minus 1. Y plus or minus, because here is the positive side here. That's the positive side, and here is the negative side. Right? Positive x's to the right and negative x's to the left. So now what I need to think about is if it's a semicircle, the area for a semicircle will be pi r squared over 2. So I just have to connect my picture to the radius. So if I look at it, this radius here, it's the green line. That's my radius. And that's exactly root y minus 1 squared. So that gives me a nice area formula to work with. Pi over 2, y minus 1. So I now get my volume will be the integral. And remember, it's with respect to y. So everything in your problem needs to be in relation to y. It would be a shame if after all that I went from negative 2 to 2. That's with respect to x. So here's the bounds with respect to y. I start at 1 and I go up to 5. So it would be from 1 to 5 of pi over 2 times y minus 1 dy. And I think I've been kind of lazy on some of the other ones, so I'll try and work this integral out just to give it a go. So this would be pi over 2, 25 halves minus 5, take away 1 half minus 1. Let's see what we get here. So 25 minus a half would be 24 halves. And then I'd have negative 5 plus 1 would be negative 4. So that's going to be 12 minus 4 is 8. So 4 pi, I hope, is my integral. So that would be the volume of this figure, whose cross sections are known to be semicircles as you go across. All right, so this time we're going to find the volume of a solid, which is bound in quadrant 1 by those, and it's an isosceles right triangle. So as scary as that might sound, it's a fancy name, but I promise you, if you do the picture, it's not as bad as the equilateral triangle. Okay, so end our course. Woohoo! End it on a high note. See if you can get through this one without any help here. See if you can conquer calculus. Okay, so let's walk through it. The good news is I didn't see anybody who didn't have it or wasn't on the way to getting there. So this is the picture you're working on, and I'll just paste it into our picture so we can talk. And the region, because it's bounded, you have to pick the spot where it's actually this one in here. Maybe I'll use green. It's this region in here that's bounded. It says quadrant 1 and between these curves. Sometimes it's tempting to pick this one, but you're not bounded here. You can go infinitely far in either of those directions, so you're not bounded. So that is the right region that you're looking for, and we're taking a right triangle when I go this way. So the base will go like this. And the height of that triangle is going to be identical because it's isosceles. So I'll do my best to come up with an identical height. Be like that. Now, if you're worried, uh-oh, what if I draw it this way? Can anybody put our worries to rest? Will it matter if it's one way or the other?
No.
How come?
The height is the volume is the same.
Well, the areas are the same. Therefore, when we add up all the areas, the volume would be the same. So yeah, we've just turned the triangle. So I'll go back to my original here. And I'm going to use it to figure out my area function. And if I look at it, these representative bars, that's my slice. It's a dy problem. So everything needs to be with respect to y. The other clue here, if you haven't already noticed this, perpendicular to the y, that's with respect to y. Perpendicular to the x, that's with respect to the x. Same thing when we go to disk and washer method. It also applies there. Whichever one's perpendicular, that's with respect to. So I'll just put that there. Okay, so I need to rearrange this. Y squared is x minus 1. So y squared plus 1 is x. And that should make sense to you because if you're looking at the base, how far out is the base? Well, the base is whatever the value of x is, right? So if this is x equals a half. So I want to know how far out I am for x, and I need you to give me the y value to get it. So it's going to be, this tells me how far out the value of x is if you give me a y. So the area here is 1/2 base times height. And if you look at an isosceles triangle, the nice thing about it is the base and the height are the same. Yeah. So this is just going to be 1/2 the base squared. So my volume will be the integral. And again, we are always used to doing x's because we started with x in this course until this chapter when we flip things around. But be careful, your bounds do not go from here to there. Those are in terms of x. Our bounds go in terms of y, which is from 0 to 5. And we have 1/2. Our base is going to be this here, y squared plus 1. And times the height, it's the same thing. So this would be what I can use to get my volume. And I guess, as I said, I'll walk through this one. Y to the 4 plus 2y squared plus 1 dy. So I'd have 1/2 y to the 5 over 5 plus 2y cubed over 3 plus y, and I'm evaluating it from 0 to 5. And I've had enough fun with fractions for one day, so I'll stop here. Okay, so hands up, you conquered it. Oh, more of you did the use. Okay, you can admit it. But anyway, There we go. That's calculus.